Ooh. Oh, hey there. Not much more American than eating a fresh grilled shrimp and steak kebab and drinking a beer. And if you're anything like me, you're left looking at your kebabs wondering, man, just how dense are these sticks? If I was trapped on an island and I had a big old pile of these sticks, could I use it as a raft to float? Could I use it as a spear underwater? All these things cross my mind. Wonder no more. With the Densomatic 9000.
Densomatic 9000?
That's right, my foreign friend. The Densomatic 9000. I know what you're thinking. Hey, that's just a wooden box screwed together with some water in it. You'd be correct. That's all it is. But using this little box and some water and one of these here kebabs, we can figure out just how dense this little bad boy is. I know you're thinking that's crazy, but let me prove it to you. Follow me to my lab. All right, what we have here is the Densomatic 9000, the kebab. Now the way we figure out its density is I place this kebab in this high-tech machine. If it wants to cooperate. And due to outside forces and forces on the stick floats.
Buoyancy.
Now, I mark the stick where the water reaches, pull it out. Once I have this mark, I'm going to measure it using trigonometry and some algebra. I'll figure out just how dense this stick is. Now, if you still don't believe me, let me prove it to you using this little device called a computer. Up here on the TV, I got the computer shooting up our Densomatic 9000 with our kebab in the water. Now, once I got that picture up there, I broke out the free body diagram. Physics term, it's okay, just keep up. We have the kebab right here, the submerged part that we measured to be 0.152 meters, and the point out of the water is 0.148 meters. And the free body diagram shows the force of the weight of the wood, as well as the buoyancy force. Now, going on the Archimedes principle of breaking out the algebra, we say the buoyancy force equals the specific weight of the water times volume submerged. We also break that again to be the specific weight of water times the area times the length, and we get this calculation right here. And once we have that, we go to the weight of the wood. Weight of the wood equals the specific weight of wood times the volume of the wood. We break that out again to the specific weight of the wood times the area times the length outside the water plus the length inside the water. That gives us our volume. Once we break that down, we have to find the y bar, which is the distance from the middle of the submerged wood to the surface of the water. We get 0.076. Once we find all that, we use what we like to call the momentum. The sum of the momentum around the hinge is equal to the weight of the wood times the distance, perpendicular distance, times the angle, cosine theta, plus, again, the buoyancy force times the perpendicular distance times the cosine angle, which gives us our total perpendicular distance. Now, do a little more algebra hoodoo. We get specific weight of wood as 7.4226 Newton meters cubed. Once we have the specific weight of wood, to find the density, all we have to do is divide that by the gravity constant, which is 9.81 meters per second squared. Doing that, we get 756.622 kilograms per meters cubed. That is how dense our sticks are.